Hey everyone, welcome back to the channel. Today we're soaring straight into the future of aviation with NASA's X-59 quiet supersonic jet, the groundbreaking QueSST demonstrator that just completed its historic first flight yesterday, proving once and for all that flying faster than the speed of sound doesn't have to mean shattering windows, rattling nerves, or waking up entire towns. This revolutionary aircraft is designed not to produce the classic ear-splitting sonic boom, but instead, a soft, muffled thump about 75 perceived level decibels, roughly the same as closing a car door from inside a house. That's the sound of the future arriving, and it could finally unlock the return of commercial supersonic flight overland, banned in the US since 1973. If you're an aviation enthusiast, a tech futurist, a sustainability advocate, or someone who dreams of cutting a transatlantic flight from 7 hours to just 3.5, you're in for an in-depth, high-altitude, low-boom journey through one of the most ambitious aerospace projects of our time. Developed by Lockheed Martin in partnership with NASA under the low-boom flight demonstrator contract, the X-59 is a 140-foot-long, 29.5-foot wingspan technological marvel powered by a modified General Electric F414 afterburning turbofan engine producing 22,000 pounds of dry thrust. It features an ultra-slender, needle-like fuselage, laminar flow wings, a T-tail, and a cockpit with no forward windshield, because every inch of its shape has been meticulously sculpted using billions of hours of computational fluid dynamics to stretch, weaken, and smooth out shockwaves before they reach the ground. From its public rollout in January 2024 to yesterday's flawless first flight from Air Force Plant 42 in Palmdale, California, piloted by NASA test pilot Niels Larsen, the X-59 has overcome years of supply chain delays, structural load testing, ground vibration surveys, and intense safety reviews to finally take to the skies. We're going to explore its revolutionary quiet supersonic technology in exhaustive detail, deliver a comprehensive technical breakdown with real-time insights from yesterday's flight, examine its critical role in reshaping global aviation regulations and commercial markets, include some jaw-dropping fun facts that highlight just how wild this engineering feat is, and conclude with the very latest developments as of October 29, 2025, including post-flight analysis, live reactions, and the roadmap to full supersonic testing. So, adjust your headset, check your oxygen mask, and let's climb to 50,000 feet quietly for everything you need to know about NASA's X-59 quiet supersonic jet. The core innovation of the X-59 isn't just going fast, it's going fast without making a scene. Traditional supersonic aircraft like the Concorde generated powerful coalescing shockwaves that slammed into the ground as a double boom, loud, disruptive, and legally prohibited overpopulated areas. The X-59 changes that entirely through a concept called boom softening, or shaped sonic boom theory. By carefully controlling the distribution of lift and volume along the entire airframe, the aircraft prevents shockwaves from merging into a single explosive pressure front. Instead, it creates a series of weaker, staggered pressure waves that arrive at the ground over a longer period, resulting in a gentle, rolling thump rather than a crack. This is achieved through an extraordinarily elongated fuselage, 140 feet from nose to tail, with a razor-sharp 3-foot-long pointed nose cone that begins diffusing the initial shock before it even forms. The cockpit is positioned far aft, and the pilot has no direct forward view through a windshield. Instead, vision is provided by high-definition external cameras feeding into a panoramic heads-up display, because even a traditional canopy would disrupt the carefully calculated airflow. The wings are highly swept at 55 degrees with ultra-smooth laminar flow surfaces that delay the onset of turbulence, reducing wave drag by 15% compared to conventional designs. The engine, a modified F-44 GE400 from the F/A-18 Super Hornet, is mounted on top of the fuselage with a diverterless supersonic inlet that smooths incoming air and shields the engine face from radar and acoustic reflection. During cruise, the engine operates without afterburner, achieving Mach 1.4, approximately 925 miles per hour, at 50,000 feet, while burning 30% less fuel per passenger mile than the Concorde did. over 600 sensors, including pressure taps, accelerometers, strain gauges, and acoustic microphones, are embedded throughout the airframe to capture detailed data on shockwave formation, propagation, and ground impact in real time. This data is transmitted live to Chase aircraft and ground stations, where it's correlated with community noise surveys to determine social acceptability. The flight control system uses advanced fly-by-wire technology with AI-assisted predictive modeling to dynamically adjust control surfaces, flaps, and even engine throttle to maintain optimal boom shaping throughout altitude and speed changes. The result? A supersonic aircraft that can fly over cities, suburbs, and sensitive areas without triggering noise complaints, emergency calls, or regulatory violations. Let's dive deep into the technical specifications and operational profile of this extraordinary machine. The X-59 measures 140 feet in length, 29.5 feet in wingspan, and stands 12.9 feet tall at the tail. Its maximum takeoff weight is 136,000 pounds, with over 60% of the structure made from advanced carbon fiber composites, reducing weight by 20% compared to an all-metal design of similar size. The airframe incorporates natural laminar flow over more than 50% of the wing chord, achieved through precision manufacturing tolerances measured in microns, which delays boundary layer transition and cuts drag significantly. The General Electric F414 engine produces 22,000 pounds of thrust in dry mode and up to 32,000 with afterburner, though supersonic cruise is maintained without reheat for efficiency and thermal management. The top-mounted inlet uses a serpentine duct to slow and compress incoming air while hiding the engine fan from direct line of sight, reducing both radar cross-section and takeoff noise to just 85 decibels at the airport perimeter, quieter than many commercial jets. The T-tail configuration elevates the horizontal stabilizer above the wing wake, preventing shockwave interference, while the vertical fin is canted outward to further diffuse pressure waves. Control surfaces include leading-edge slats, trailing-edge flaps with variable camber, and all-moving stabilators, all driven by high-speed electromagnetic actuators capable of making micro-adjustments thousands of times per second to maintain precise lift distribution. The cockpit is a digital marvel. Dual large-area touchscreen displays, voice and gaze-based command inputs, and a synthetic vision system that stitches together feeds from multiple external cameras to create a seamless 180-degree forward view. The pilot wears a helmet-mounted display that overlays real-time boom prediction maps, atmospheric data, and system health diagnostics. Structural health monitoring is built in, with fiber optic strain sensors embedded in critical load paths to detect fatigue or damage instantly. Yesterday's first flight, which lasted 31 minutes, began with a standard takeoff roll from Palmdale's runway 12, rotation at 150 knots, and a gentle climb to 15,000 feet. The aircraft performed gear and flap cycles, basic handling checks, and a low-speed pass over the field before transitioning to Edwards Air Force Base for landing. All systems, including flight controls, hydraulics, avionics, data links, and environmental controls, operated within 1% of predicted performance. Chase aircraft, including a T-38 and an F-16, provided visual observation and high-resolution photography. Ground crews at Edwards are now preparing for Phase 2. High-speed taxi tests, flutter envelope expansion, and the first supersonic acceleration, targeted for January 2026. Side. The strategic importance of the X-59 extends far beyond NASA's test ranges. For over 50 years, the FAA and most global regulators have maintained a blanket ban on civil supersonic flight over land due to sonic boom concerns. This has confined next-generation supersonic aircraft like Boom's Supersonic's Overture or Ariane's AS-2 to overwater routes, severely limiting their market viability. The X-59 is NASA's scientific battering ram to break through that regulatory wall. By flying controlled, instrumented overflights above selected U.S. communities, starting with cities in Texas, New Mexico, and California, and collecting both acoustic data and public feedback, NASA aims to build an ironclad case that a 75 PLDB thump is socially acceptable. This data will be submitted to the FAA, ICAO, and EASA to support the creation of new noise-based supersonic certification standards by 2028. If successful, it could unlock a multi-trillion-dollar global market for supersonic business jets, regional airliners, and even transcontinental passenger services. Imagine flying from Los Angeles to New York in under 2 hours, Chicago to London in 3, or Singapore to Sydney with just 1 refueling stop. The economic impact would be profound. Reduced travel time for business, boosted tourism, and new manufacturing jobs in aerospace. Environmentally, the X-59 sets a high bar. Its fuel efficiency, low takeoff noise, and absence of afterburner in crews make it far greener than the Concorde, and future commercial derivatives could incorporate sustainable aviation fuel or hybrid electric propulsion. NASA has already selected 6 initial test communities, deployed ground microphone arrays, and launched public education campaigns to ensure transparency and buy-in. International partners, including JAXA in Japan and DLR in Germany, are collaborating on boom modeling and atmospheric propagation studies. The ultimate goal? A new chapter in civil aviation where speed, sustainability, and community acceptance coexist. Now for some truly mind-bending fun facts. First, the X-59's sonic thump is so soft that it's quieter than a household vacuum cleaner measured from 50 feet away, and over 100 times weaker in pressure than the Concorde's boom. Second, the aircraft's nose cone is so sharply pointed that engineers had to design a custom 3D printed latch mechanism for the canopy to avoid scratching it during maintenance. Third, the shape of the X-59 was optimized using over 1 billion hours of supercomputer time, more computational power than was used to put humans on the moon. Fourth, the pilot's forward vision system uses the same camera stitching technology found in high-end smartphones, but with military-grade redundancy and radiation hardening. And finally, the X-59 is the first X-plane in decades to be designed from the ground up with community noise as a primary performance requirement, not just speed or altitude. As of October 29, 2025, the X-59 program is officially in flight test. Yesterday's maiden voyage was declared a complete success by NASA, Lockheed Martin, and the U.S. Air Force. NASA Chief Bill Nelson hailed it as a giant leap toward bringing supersonic flight back to the world, quietly. The aircraft is now housed at Edwards Air Force Base, where technicians are downloading over 10 terabytes of flight data for analysis. Preliminary reports indicate all systems performed within specifications, with no anomalies in flight controls, engine operation, or structural loads. The next major milestones include high-speed taxi tests in November, first supersonic flight in January 2026, and the start of community overflight campaigns in the spring. NASA has confirmed that ground sensor arrays are already in place in Galveston, Texas, and Lancaster, California, with local outreach events scheduled to explain the project and address concerns. Minor issues identified in pre-flight wind tunnel testing, such as inlet duct resonance at certain angles of attack, have been fully mitigated with acoustic damping liners. GE Aerospace reports the F414 engine operated at 99% of predicted efficiency, and Lockheed Martin is preparing a digital twin of the aircraft for real-time performance modeling during future tests. With over 5 years of assembly, thousands of hours of ground testing, and international collaboration, the X-59 is on a clear path to delivering its final regulatory report to the FAA in 2028, potentially lifting the overland supersonic ban by 2030 and enabling a new era of high-speed civil aviation. The X-59 quiet supersonic jet is more than an experimental aircraft. It's the sound of possibility arriving softly, the blueprint for a faster, quieter, more connected world. What do you think? Are you excited for the return of overland supersonic travel? Do you believe 75 decibels is quiet enough for daily flyovers? Are you curious about how this tech will scale to passenger airliners? Drop your thoughts, theories, and predictions in the comments below. Give this video a like if it broke the sound barrier for you in all the right ways. Share it with your fellow aviation enthusiasts. And if you haven't already, hit that subscribe button and ring the bell so you never miss a deep dive into the technology shaping tomorrow. Thanks for flying with me today, and I'll see you in the next one.